Lipstick.
Mommy, you look beautiful.
Okay, let me see what you did now. Show me.
I'm already recording. It's happening. So, Mommy, I want to take this video because I want to record you talking about your amazing test.
What do you want to know, Sarah Beth?
I mean, you always just talk to me about like stuff I can't understand. Aneuploidy, blah, 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 blah. So,
But you have to ask me specific questions. I can't just give you a lecture.
well, I mean, you,
Ask,
you
ask me a
constantly give me a
question.
lecture.
Ask me a question that's meaningful, and I'll give you a response. But for me just to spout BS, I'm not prepared to do that. So give me a question. What do you want to know about the test?
Mom,
What does it do?
okay, Mommy, how about this? You told me just now that your test has so much science behind it, it's the gold standard, that it's very accurate, I believe is what you said. So could you tell me a little bit more about the tests right now you did for early detection of lung cancer? Can you talk about it? How it's working in China? How does it work in terms of the science?
Well, these are very big, open questions, Sarah Beth, about how it works according to the science. Basically, the basic premise is that every cancer, no matter how small, even when the cancers are in situ or in situ, that they haven't gone through the basement membrane, have the ability to cause circulating malignant cells to go into the bloodstream. So it actually doesn't really matter on the size of the tumor. You can have very big tumors, very small. You can even have metastatic tumors, but you can get large numbers of circulating tumor cells. And the trick is to be able to do a blood test to be able to pick up in passing these circulating tumor cells to identify them as being malignant, and then to be able to say that this is coming from a cancer in the lung.
Okay, so basically, you told me just now that you only do this, you don't just take blood from random people, you have to take blood from someone who already has nodules, right?
Well, if you had to just take 1,000 random people, you might pick it up in 2% of people, but that would be a hell of a waste of your resources.
Mm-hmm.
And you'd have to do 1,000 tests to pick up two,
Mm-hmm.
because it depends on the prevalence of lung cancer. Like how many people walking around in the street, you don't think there's anything wrong with them about
Mm-hmm.
lung cancer. So people don't do tests that way.
Mm-hmm.
It's not a screening test. Right now, it's what we call a diagnostic test. Diagnostic test means that there is something already in the lung that was picked up by a low-dose CT scan,
Mm-hmm.
and the question that the radiologist has, or the clinician, most importantly the patient, wants to know: Am I walking around with a highly lethal tumor that's going to kill me soon, or is this just benign and I can leave it alone? And the test is to say, listen, you don't have you don't have cancer because we didn't detect any circulating tumor cells, or hey, listen, it's suspicious because we're getting a few cells that are not normal
Mm-hmm.
and therefore investigate it further. That's the whole premise of the test.
So you have someone with a suspicious nodule, you take blood from them, and then what do you do with that blood? Could you go through like the more technical aspects of how you do the test, what you're looking for? You're doing fish on the test. What does that mean?
Okay, so when you say suspicious nodule, we can even do this on nodules that are as small as 5 millimeters, tiny. The lungs are big. So you can have a very tiny nodule that is picked up on what we call a low-dose CT scan. And even the best radiologist in the world can look at it and say, listen, I don't know what it is. Come back in 6 months. If it's growing, if it's getting bigger, or if it has certain characteristics, then we probably need to biopsy it.
Mm-hmm.
Okay, so that's the first thing. Secondly, if you took 100 people, or maybe 1,000 people, and you picked up nodules in these people, know that 95% of them are benign, that only 5% of these would be malignant.
Mm-hmm.
So the thing about the test is we want to say this is dealing with a malignancy. That's what the purpose of the test,
Mm-hmm.
to pick up these cells. How do I do it? How is it done? What's the background for it? Is that what your question?
I want to know, like, what the fish is testing,
Okay.
like the,
Okay, so you have to
what are you
understand.
analyzing in the genes? What are you
Okay,
looking
all right.
for?
So what I'll tell you is that normally we have 46 chromosomes, right?
Mm-hmm.
And we have about 30,000 genes that are important. Okay. Normally, if you do something called fluorescent hybridization, in situ hybridization, and you had to look at all the chromosomes in the genome. You had probes for that. You would just see like 46 dots, right? Because each chromosome there would be two copies. It would be like two chromosomes. If you looked at what they called the centromeric areas. As soon as you start getting additional chromosomes, or two additional chromosomes, you're dealing with a malignancy. Because one of the bases of cancer is it's got chromosomal instability, or what we call aneuploidy, uneven numbers of chromosomes. So that's the basic premise of this test. So what did we do? How did we know which tests or which genes to look at? We took a consecutive series of patients with lung cancer. I think there were 33 patients who had lung cancer, early stage lung cancer, that were resected at MD Anderson Cancer Center. We took out the tumor. We took slices of the tumor, making sure that there was tumor there. We extracted the DNA from, and some were adenocarcinoma, some were squamous. This is what we call non-small cell lung cancer. Took out the DNA, looked at what's known as the cDNA, or the coding DNA, and we compared it with normal lung. And we put everything on what we call microarrays. Microarrays, with their genetic microarrays. So they have imprinted on them all the genetic sequences of 30,000 genes. So we put on the normal DNA, right, from normal lung, and then we put on, and this is from the normal lung of the patient, and then we put on the tumor DNA, and we did something called subtractive hybridization. We came up with about 300 genes that were altered. 300 genes that were altered from the
So you
normal.
compared the normal DNA to the mutated DNA, or the different DNA, and you said these are the ones that are different. You canceled out all the ones that were the same.
Okay, and then we thought, oh, this is very interesting. Some of them are deleted. Some of these genes have been lost, and others have been gained. And in about 100 cases, they were, they were the same between adeno and squamous carcinoma. So there was a lot in common between them. So we wanted to see genes that were universally deleted in adeno or in squamous carcinoma. And usually deletion of genes usually refers to tumor suppressor genes, a gene that holds the proliferation in check. Like, in other words, you have a lot of genes. Your cells are very complicated. The definition of cancer is unchecked growth, right? It's a cell that just decides to do its own thing and go crazy and start growing, and then its progeny multiply, and its progeny multiply. And in a few months' time, you've actually got like a little mess. And then these cells acquire characteristics that make them invade into the bloodstream. So what is stopping all this stuff from happening? It's a very complex, delicate mechanism in your cells. It's called tumor suppressor genes. So we were looking for the earliest sign, the tumor suppressor genes. And we came up with about 100 different candidates. And what we found was we wanted something specific for lung. We came up with surfactant protein gene. Surfactant proteins are unique mostly to the lung. Surfactant protein is what makes your lungs expand. Surfactant, when you're a baby, when you take your first breath, your alveoli in the lung are coated with surfactant, and it allows the alveoli to expand, right? So we thought, oh, it's interesting because surfactant A, B, and C, and D, all the species, all the subtypes of surfactant were deleted. That's very interesting. So why don't we just choose surfactant protein gene as one of them? And then the other gene we chose was on 3p22.1. The reason we chose that one was in all the literature that ever looked at lung cancer, they always said that particular region of 3p is very important. In all lung cancers, we see that there's something going on. And we had to choose a gene as well that other people hadn't chosen, that other people weren't using in their research, that other people didn't have patents on. So we chose 3p. And then as a control, when you do FISH, you need to have a control. We chose the centromeric 10 and we chose centromeric 3. Okay, because you have to have a control to say you've got extra copies or you're losing
You
it.
need like the baseline.
Right, so you normally have 2 copies of chromosome 3, but if you had 3 copies of 3p22.1, you'd know that you've gained one because you've only
You
got
mean you
two
usually have
copies.
2 copies normally.
You normally have two. Or
Hmm.
if you lost it, then you'd know that you were losing it.
But
If
didn't
you
you
got
just
two
say
copies
that?
of 3,
Hmm.
2 copies of centromeric 3, and 1 copy of 3p, it means that somewhere it was lost. So you
So,
lost it.
so the centromeric one will always have 2, and
Yeah.
compared to that, you can see, oh, it's gained 1, so it's
Or it's
3,
lost.
or it's lost when it only has 1.
Yeah. But
But
when we actually did our test, we copied another test that still is very popular by Abbott Labs, and that's a test for bladder cancer called Eurovision, and that said in order to call a cell malignant, you have to show that there are 2 extra copies in each. You've got to have 2 extra chromosomal copies. Okay, not just one, but two, to call it to be absolutely positive.
what's a
So we're looking
double?
for a
So instead of
gain.
2, you're looking for 4?
Yeah, so we're looking for gains of not just one but two. In other words, normally in a multiplex 4 color fish, in a normal cell, you're only going to get 8 signals.
Because 2 times 4.
Right. Now, if you get 9, it means that one of the gene was you got an extra copy.
Mm-hmm.
You had a gain.
Mm-hmm.
But if you have 10, it means that you've got 2 extra copies.
Mm-hmm.
It means that you've probably got an extra chromosome there, a whole extra chromosome.
Mm.
So that's what we were looking for. So our criteria is in order to call a malignant cell a circulating tumor cell, you have to have at least one whole extra chromosome in there, which would be manifested by 2 extra copies. In other words, it's called aneuploidy. Ploidy is the normal copy number, which is diploid. Haploid means half the copy number,
Mm-hmm.
and aneuploid means an uneven copy number. So we insist on 2 extra copies. So it's a very stringent test because you have to have a whole extra chromosome gained, either a whole extra chromosome 3 gained or a whole extra chromosome 10 gained.
And you're saying that the results have been pretty accurate so far?
Well, it's very unusual for a person to be walking around with cells that have got extra chromosomes in them.
Mm.
In order for that to happen, either you've got some congenital abnormality, like like a triple X, like some men are born with 3X chromosomes and 2Y. They're usually criminals. It's a very weird phenotype. Or you can be some sort of mosaic. You've got some genetic abnormality, or you can have like a Down syndrome has got 3 copies of chromosome 21, right? And these people who've got Down syndrome have a very high tendency to get malignancy. They've got extra chromosomes. But this is germline. They're born like that in the germline. But what we're talking about is acquired somatic. It's in the somatic cells. It's not in the germline. Your body's made up of the germline, like from your ovary or sperm, and you're talking about somatic cells, which is in your organs and where cancer rises from somatic cells. And normal cancers are because you've got smoking, you're inhaling these carcinogens and the tar and the nicotine, and it's at very high temperatures, and it's damaging your DNA and causing abnormalities in the DNA, and therefore you start getting extra copies of this and that. Okay, Sarah Beth, I think it's time to take a break because what else is this? What do you want to know? So we started with the baseline, and we looked for these extra copies, and we saw that it was happening in the blood. We concocted a 4 color fish probe, and then we started to do it on patients, and lo and behold, we were quite accurate, and we saw that our hypothesis was correct. That per people, because we had seen this in the lung cancers, that they were having these tremendous disturbances of different chromosomes. We happened to be very lucky. We picked the right ones, and we saw that it manifested as circulating tumor cells.
And who else did you work on with us?
Okay, so I could never have done this without Feng Zhang, who was this brilliant guy who came into my lab one day. I had just got this amazing grant of $1.5 million. I had first time I ever wrote a grant, and I couldn't believe I had it, and I knew that fish was the thing. I didn't know what I wanted to do with it, but I knew that the technique was good. And this man who could hardly speak English stumbled in and told me that he had studied in Switzerland with a very famous group, the Calaminis, who had actually, um, they were the father, or they had invented fish, and they were the world experts. And he was a urologist from China who had got his doctorate in science from Switzerland, from Basel. They were the Calaminis, I think, were from Basel, and then he was working at Science Park in near Bryant, not Bryan, yeah, Science Park, Bastrop, and he wanted to come to Houston to the medical center, and he heard that I was looking for somebody, so it was like a match made in heaven. I gave him free reign of the lab. He got all sorts of boxes of DNA probes, and he was in his element, and he was discovering things left, right, and center. And he was the one who did all this hybridization. And we've written papers on this, of course. And we came up with this panel. And then at the time, we were just doing it in sputum and in washes from the respiratory tract. And then I saw in the sputum of patients in the inflammatory cells, not even in the epithelial cells, that the neutrophils of the blood had all these abnormalities, the same as in the epithelial cells. And at the time I said, wow, how does that happen? And obviously it must be in the blood, because these are blood cells that have got it. And they're coming from the blood into the sputum. Because when you have lung cancer, you get a lot of neutrophils, a lot of inflammation. And I remember saying to Abba, who was my tech at the time, listen, Abba, this has got to be in the blood. So we got hold of blood from a patient with cancer, small cell lung cancer. We did the normal thing that I do for lymphoma. I did a lot of lymphomas this way. The Ficol high-pack gradient separation, took out the buffy coat, and we hybridized the cells in the buffy coat with the 4-color fish. And lo and behold, she called me to look in the dark room, and she said, Dr. Katz, I don't think I'm seeing anything. And we'd also stained with CD45 and lymphoid marker, and I suddenly saw all these lymphocytes, so-called lymphoid cells, had all these weird abnormalities as well as negative cells. So not only were the tumor cells had this, but also cells that were staining with CD45 had them. And this was the most amazing thing. Subsequently, we stained with stem cell markers that the stem cells had them, and we stayed with EMT markers, mesenchymal markers, and it was snail and zeb and all those things, and we showed that these had it. So we suddenly saw that in early lung cancer, the reason my test is so successful, we don't do what the conventional thing is to look at CD45 negative cells that are non-lymphoid cells that are expressing EpCAM and cytokeratin. We look at everything. We just go for all the cells, no cell left behind, look at all the cells, and we suddenly see that all these cells are manifesting these changes because these are stem cells, and these are tumor initiating cells, and these are pluripotential cells, and eventually they turn into malignant cells. I mean, fully fledged malignant cells. And at that point, Sarah Beth, we can take a break. Okay?
But were you the first one to discover this?
Yes.
And how long ago was this discovery?
We published this in 2010, and it caused an absolute furor. People didn't believe it, and I had a national press conference. I also remember going to Holland to give a workshop, and the guy literally kicked me out. He told me that I was full of BS. This is the guy who had a competing technology called the cell search. His name was von Tapperen. I've got it on my papers.
Maybe don't tell me. I don't want to be
anyway,
super liable.
Yeah, they didn't believe me, but a lot of people did believe me. And afterwards they came up and they were so sympathetic. They said, we believe you, don't worry about him. Because he had vested interest. He had a big commercial thing.
Wait, tell me the story about you're in a lecture, you're in the audience, and what happened?
No, that's a different story.
Wait, tell me that story.
No,
I love it. No, I love that story. No, tell me the story.
No.
Tell me the story.
No.
You were at a lecture. You're in a lecture, and you were sitting in the audience, and someone was lecturing, and what happened?
Why do you want to talk
I love
about
this story. It's like a story that is one of my favorites.
Well, this was.
Was it about a different test?
It's about lymphoma. I was doing lymphoma by fine needle aspiration.
When?
Many years ago. I started in the 90s. I was pioneered that at MD Anderson.
Mm-hmm.
And people couldn't believe I was doing that. So I was invited to go to Australia to talk about this. I was a keynote speaker. And I decided I'd wander into some of the other sessions that were based on tissue, not based on fine needle. And I sat at the back, and I thought, there's a very good speaker, very famous. I'll sit down and I'll listen. And I'm sort of half sleeping, and suddenly a slide comes up, and my name is on it. And I thought, what the hell? They didn't even know I was in Australia. I mean, there's a guy from Hong Kong. He didn't even know who I was.
But you're a keynote speaker. You don't think he saw that you're a keynote speaker there?
Maybe, but I'm sure he didn't expect me to be there. I mean, it was just a total coincidence. And then he said to me, Ruth Katz, she thinks that she can diagnose lymphoma on a fine needle aspiration. I mean, we can't even do it on a needle biopsy. And she says this, and she says that, and she says this and this and this, and really like he'd never met me, and really like condemning me and talking lies and rubbish about me. And I thought, oh my God, what am I going to do? I mean, I was terrified. There were like literally 1,000 people in that room. It was a huge hall. It was a plenary. And then they said, and I think, no, I've got to defend myself. I've got to defend myself. So when they said, are there any questions? I stood up and I went to the microphone and I said, Dr. Chan, I want to tell you that I am Ruth Katz from MD Anderson. And I remember what happened in the hall. It was like a wind blowing through the, like everybody turned around and they went, like I heard all that condemnation about me. And then there I was standing up and saying, here I am. And he said, and then I said, I actually think I said, you should be ashamed of yourself talking about me that way without knowing. I said, you should be ashamed of yourself. I said, this is absolutely untrue. And I said, whatever I've said is based on truth. We aspirate lymphomas. We do a cell count. We get millions of lymphoma cells. We put them through flow cytometry. We do immunocytochemistry. We show that they're clonal. We do proliferation markers. We show whether they're indolent or whether they're aggressive. We do this. We do that. We have a fantastic report. It's just like a biopsy. It gives you equivalency. And when they do the biopsy, it's exactly the same result as we have. And I went on, and the moderator who knew about me, Peter Gascoigne, hated me, said, all right, Dr. Katz, we've heard enough. You can sit down now. And then afterwards, when I went out, strangers came up to me and they said, oh, are you Ruth Katz? Congratulations. We heard you. Wonderful.
Well, Mom, that sounds like you. It's one of those moments you wish you had like social media back then. There would have been like.
Anyway.
Well, that's a good story. Thank you for sharing it.
Sure.
Well, wait, one last question. So your test, the one that you created, the circulating tumor cells.
When I die, Sarah Beth, you can play this at my.
I will. I'm planning on it. I mean, Hassa Khalila. I don't mean that. I just want to have it on the record.
Yeah.
But were you the first one to discover circulating tumor cells?
This type, yeah. No, I wasn't the first. People had seen them many years ago. I was the first one to do this test and to show there were so many thousands. That's why people couldn't believe it.
Mm-hmm.
That's why the guy, Leon Vertapestein from Holland, that's why he couldn't believe, because he was finding 3 or 4 cells with his method. I was finding thousands.
Well, what's the difference between your methods?
I just explained to you. They do it on a magnet, and they look that these cells have to have cytokeratin and EpCAM, but they don't realize that in early lung cancer, most of the cells are like primitive stem cells that haven't yet developed that.
Mm-hmm.
The cells that are going out, they can't have that. They have to slip out of the tumor and get into the bloodstream and lose all these desmosomes and things. Biologically, I looked at the biology. I was a very biological, science-based person. It wasn't feasible to do it that way. Biologically, it doesn't work that way. Only when this test is good if you have advanced. When you have advanced lung cancer, you can get all these EpCAM and cytokeratin. For early, you just get what I found.
And so your test has been licensed by whom? By where?
Well, my test was sub-licensed by a company called Lung Life AI in California, who in turn sub-licensed it to a company called Sanmed Bio, which is like a sub-company of a very big pharma company called Livson, Livzon, Livson Pharmaceutical. It's like the eighth largest pharmaceutical company in China. It's like $1 billion company in China. But this Sanmed, luckily for me, is that they really believe in me. I'm a consultant, And they have a guy called Dr. Bai. He's very excited by my test. He's like the doyen of pulmonologists in China. And so the tests that we're now proposing, as I have on my slide, you haven't seen on my new graphic, is he's getting 1,000 hospitals, which is easy in China. Each hospital will send 100 tests, and we're going to do the 100,000 real life. So it's not going to be clinical trials, it's going to be real life test of my CTC test.
Amazing.
And this is coming up for this year.
And they're not being manually counted, all the little dots on the fish, right? So you have an artificial intelligence component.
Well, initially they were manually counted, and manual counts are not good because A, they were looking at thousands of cells, very tedious, very easy to miss something if you had a bad day, fighting with your husband, your boyfriend, you're distracted, very easy to miss a few cells. However, now they've got the algorithms, they've trained the machines. A, it's quicker, and B, it's a lot more accurate, much faster.
And does this have to do with BioView?
Well, they're using the BioView data, yeah, but it's like GE, General Electric, and the Chinese artificial intelligence company. And it's also going to be integrated with feature extraction on the CT scan on the shadows to see if they can make a better diagnosis for lung cancer, whether there's something in there. They will train the machine with deep learning, and the machine will be able to give a better opinion, and they'll integrate the fish with that to come up with a more accurate diagnosis.
Amazing, Mommy. I'm very proud of you.
Thank you.
I guess that's the end.
Yeah, well, how long was that? About an hour?
No, 26 minutes. Okay,
No, I want to go inside.
Okay, bye.
Bye.
Any last words? Any last thoughts? Wait, give it a second until this
What
is...
sort of last thoughts could I have? I've had an extraordinary career. I enjoyed every minute of it.
Wait 1 second. Wait till this is done going up. Okay, say it again.
I said I've had an extraordinary career. I'm now starting on my second career because thanks to you, Sarah Beth, I'm applying to be a Professor Emeritus from MD Anderson, which I should have done, but I never did. But considering what I plan to do now, is that I also going to get my medical license in Israel, so I can go do research at Tel HaShomer and work on liquid biopsy. I've just written a very big, intensive book chapter on it, and hopefully I want to establish a fellowship in liquid biopsy because this is a transformative technology. It's an amazing technology, very easily accessible for people with cancer. Gets rid of...
But didn't you retire, Mom? When did you retire?
I never really retired. In my mind, I've always been active. I'll never retire. When you put me in the ground, I'll be retired. But I'm not retired. I read extensively. I follow the literature, and yeah, I know I'm a lot on Facebook. I shouldn't be, but I'm not retired. No, not mentally anyway.
Sorry, you're saying you're going to make a fellowship. So why are you making a fellowship?
Because I think that people who are either pathologists or oncologists need to know a lot. They don't know very much about the subject. It's huge. I'm not going into that now, Sarah Beth.
Which subject? Liquid biopsy?
No, what I plan to do with this fellowship. I'm not talking about that.
It's under wraps. Top secret.
It's top secret, yeah.
Okay. Thanks for sharing all your knowledge, Mom. I appreciate it.
Well, that's it. Thank you.
Okay.
Bye.
Bye.